Okay, so today I want to start our journey into developing programming languages. And we're going to do this starting with the sort of core center of most programming languages, which is arithmetic, right? We normally always are adding and subtracting numbers, and so that's sort of like the center of almost any programming language. So we're just going to develop using syntax and semantics, the basics of arithmetic, right? So I want to talk about the operational semantics of arithmetic. Right, so this means that I want to come up with my abstract grammar, and I want to have some semantic rules over here, which will give meaning to the abstract grammar. And what do we want to be able to represent, right? What are we talking about? Well, we want to be able to, write down something like log of 1 plus 2 times y, where we have some sort of bound value for y, and be able to return a number. Right, so again, remember we have a basic parser that will take this and turn it into our abstract grammar. We're going to be the parser for now because it's straightforward enough. And then we want an interpreter to be able to take that abstract form, right, the AST that represents this, the abstract syntax tree, and turn it into an actual computation using the semantic rules. So, what is our abstract grammar to start with? Well, we're going to have expressions, right? This is an expression. Inside the parentheses is another expression. This is an expression. All of the tiny component bits of any of an arithmetic expression is going to be an expression in our language. And this can turn into, well, it could be, we're going to call it an ident of a string. Right, this is going to be like this y in here, so it's really just a placeholder for some value that's going to be stored in what's called the environment, which we'll get to when we talk about the semantics and the evaluation function. So we can have some sort of variable name. We could have a constant. It's going to take in a double. And it just represents that double, but in our abstract language, so we have to wrap it in this keyword to sort of signal that we're not talking about or actual numbers here. We're talking about this abstract concept of a const, right? That'll be transformed by our evaluator into the double that it contains, but here it's just a abstract container for a number. And everything, all of our values in this world are numbers, right? Because we're only talking about arithmetic. So you don't think about anything, you don't have to worry about any higher types or anything like that. So we have ident, we have constant, we'll have plus, and this was going to take a E1, expression E1 and an expression E2, right, and that should be returned the addition. We'll have minus, again, it's a binary operation. We'll have mult, and we'll have division. We can have the exponential function takes a expression and it returns e to the whatever e evaluates to. And then we'll have log, right, the inverse of the exponent function, which takes an expression e and will compute the log of it. We can have more things like we could have sine, cosine, but this is enough of a fragment for us to work with. If you want to see the fuller expression, right, we have that in the Jupyter notebooks that you can play around with. But this is enough to at least represent our target sentence here. So using, right, this format, we can rewrite our concrete syntax up here into an abstract syntax format, right? So this is going to be log of plus of const of 1.0, and what is it adding? We're adding 1 to 2 times y, so we need a mult of const of 2 and ident of y, and then a bunch of closed parentheses. Is that enough? Got ident mult plus log. Right, so this is what we want our evaluator to be able to understand and eventually return an actual number for it. So what is the evaluator, right? It's a function, right, eval. It's going to be a function that takes in an expression and what's called an environment. This is going to be a map of basically strings to doubles. And it should return a double. I've written this up in essentially Scala notation. But what is it doing, right? The idea is that you take an expression in, and the environment, what is this map? It is going to be able to resolve these idents, right? So the whole idea of ident is it's a variable name where y is associated to some number, and that's what a map does, right, in Scala. It will, or it's basically a dictionary, if you like the Python terminology, and it will take a string. It's a set of key value pairs of strings pointing to doubles. So, for instance, in our case, maybe the map is just a single thing that says that y points to, let's say, 1.2, right? And so the eval will take in this expression and take into account the fact that y actually should be replaced by 1.2, and it should be able to go through all of these rules recursively. So, right, it's going to first take a look at this whole thing, and it's going to say, oh, I see that that's a log of e, so I should do whatever my big step semantics say to do in that case. And to do that, I need to figure out what the value of e is. Well, e is this interior chunk of the plus, right? So e looks like a plus of e1 and e2, which we'll have rules for that say exactly how do I resolve this, right? I did a little example of this in the first week, but we're going to go into more detail here. Likewise, the plus contains e1, which is a const of 1.0. So we need a rule that says what do we do when we see a const. And likewise, we see a mult and another const, and we have an identity, and so we have to come up with rules for eval that will evaluate each one of these things in turn. And then eval will just recursively call itself to get all of the component parts it needs, and then it will recombine all of those and return a number. All right, that's why we just have a double here. So let me make a little bit of room over here. Let's look at a couple of these simple rules. So, like perhaps the easiest one, right, is what does eval do when it sees a const of some, well, it has to be a double, right? So let's call that x. So big step semantics, right? We always have this big line, and the idea is that in order to define this bottom left corner, we need to do everything on the top line. It has to, whatever happens on the top line has to be true, and that'll give us the component parts to answer what should be on the right-hand side of this equal sign. In this case, there's really nothing to do, right? Because we're given all the component parts that we already need. And eval is going to take this constant whose actual value is x and just return x, right? So you can see eval, and actually we should have this under an environment. This will just give us x, right? So in this case, our expression is basically the simplest expression we can even think of. Our environment is, let's continue with this map here, and we return a double. X is just a double in this case. So there's no upper rule, and that's fine, right? If there's nothing to do, there's no prereqs that we need, then yeah, it's just empty there. Let's say plus. So what's the rule for eval of plus of e1 and e2 under some environment? Well, to figure that out, right, I need to know what does e1 and e2 evaluate to. So we want to eval e1, and that should hopefully return something. Let's call that v1. And as long as that's a real number, right, a double, then we're happy with that, because obviously I can't add two numbers that aren't numbers. We'll see this with error cases, right, where we'll want to make sure that if there's an error comes up, we don't just start adding errors together unless we know that errors can absorb other errors. But yeah, it's always useful to sort of point out that this needs to be a number. And likewise, we're going to have eval of e2, and let's call whatever that returns v2 should also be a number. So if, right, we know that eval of e1 under our environment is v1, and we know that e2 under our environment evaluates to v2 and is a number, then we know what the eval of plus of e1 and e2 under the environment should be, right? It should just be v1 plus v2. Pretty straightforward so far, right? Okay, let's do multiplication. So we have eval of mult of e1, e2 under our environment. What should this be? I mean, obviously it should be whatever e1 and e2 evaluates to, right? So on top of our bar, we pop in eval of e1 under the environment is going to be v1, and that should be a number, and eval of e2 under the environment is going to be, say, v2, which is a number, and the final result should be v1 times v2. Now there's another way we could do this, right? So this says that regardless of whatever the left-hand, right-hand sides are, we're always going to be evaluating both of them. But we could, realize, maybe try to be a little more clever, and realize that if multiplying, right, I have 0 times something, right, regardless of what that something is, this is always going to be 0. So in this rule, right, I am always evaluating both e1 and e2, but I could, try to be a little slick and say, well, what happens if I know that e1 evaluates to 0, I know what this is going to turn out to be. Right, the total result's going to be 0 regardless of what e2 is. So I could, do number 1 as my definition of multiplication, or I could do something like this, right, e1 times, or mult of e1 and e2 under an environment. Well, if eval of e1 is 0, right, then let's just return 0. Of course, this isn't all the possibilities. We also have to add, and what happens if e1 is not 0, right? So then we also have that eval of mult of e1, e2 under the environment. Let me change pens here. Right, that'll be eval. Ooh. One of these will be, there we go, of e1 and which should be v1, and that should be not be 0, right? But it should be a number. And then we also want to eval e2 under the environment, and that should be v2, which is a number. And this should then return v1 times v2. Right, so this is version number 2 of the multiplication rule. Either of these work, right? In some ways you could think that maybe the second version is nice, because we are sort of taking advantage of the fact that saving computation. Right, I know that if I'm multiplying, if the first thing is 0, then I don't have to evaluate the left or the other half. And this is what's called short-circuiting. Right, because we are not evaluating part of our circuit, right, our computation. And this can be useful. We'll see in a future lecture where we actually do want to do short circuiting. But it could be tricky here, and in fact, most programming languages don't short circuit multiplication. Partially because, right, well, let's look at a couple of examples, right? We could have something like 0 times 100 divided by 0, right? This will evaluate to 0 under our second rule here, our short-circuited version. Even though, right, maybe you'd want this to evaluate to be some sort of error term, and then multiplying an error term by 0 should still sort of give you an error. In our version 2, this will not, no errors will be caught here, right? Because we'll see a 0 and then we'll just return 0. So, I mean, maybe you're okay with that idea that maybe these zeros can cancel, depending on what sort of mathematical structure you're using, right, for division by 0. But there's more complex things, right? Because we could have 0 times, well, E2 is an expression, so it could be a wide variety of things. And right now, you know, our language only deals with arithmetic, but in more full-fledged languages, right, it's an expression is basically anything between curly braces. So we could have a bunch of things, like we could have some print line statements, right, that change the buffer that's going out. We could write to some file, right, to some f, and then some other messages there. We could maybe update a variable, right? Let's change t to be plus equals t. Right, and if we use the second rule, the short-circuited version, well, none of this is going to happen, right? Because we're going to first see a 0, and then we're going to completely ignore the second block, right? So this was E1, and then this whole thing is E2. And this is what's called side effects. Right, so these things, each one of these is a side effect that this block of code does, because it's modifying something outside of the block of code. We say some code is side effect free if everything that it does is contained within that block of code. There's no external reaching, right? There's no connecting to, say, the standard out. There's no writing to files. There's no changing mutable variables. All of those are side effects. So one issue with short-circuiting is that we might skip some side effects that we actually want to do, right? Perhaps we actually want to print these things out, and if we have a short-circuited rule like this, we're going to just completely avoid them. And that could be troublesome. So in general, for something like multiplication, we use a rule like number 1 as opposed to number 2, just to avoid missing side effects. Of course, side effects, I mean, they're not necessarily bad, they're not necessarily good, right? Side effects can't be avoided in some cases. Functional programmers, you'll notice, will be often described as doing stuff side effect free. And that's one of the benefits of thinking functionally, is that you can kind of avoid side effects as much as possible. Of course, in a large data or code base, you can't help but have side effects, right? Somebody needs to be listening to how your variables are changing sometimes. There's a lot of concurrency that might be going on, situations where you just can't avoid side effects. But it's useful to be aware of exactly what side effects you're dealing with. Let's do another rule. So let's do division. Right, so if we have E1 and E2 under an environment, what should the division rule be? Right, well, we have our big step, and we're going to have to evaluate E1 under the environment. And that should be v1, right? A number. And we should also evaluate e2 under the environment. And that's v2. And that should be a number, right? Well, can it be any number, right? We're doing division here, and what's sort of the classical caveat, the thing you want to watch out for? Well, obviously, division by 0, so v2 should not be 0. That's a little off the screen, so let me write this up, hopefully with a stronger color. So this should be v2 not equal to 0. In that case, what should our division rule be? This should just be v1 divided by v2. Right? And one thing you want to watch out for when writing these semantic rules, right, is to make sure that you cover every single possibility. Right? So here we have the case when e1 is a real number, and the case when e2 evaluates to a non-zero real number. But we also have to take into account the case, right? Eval of division, e1, e2, and this pen is dying as well. All right, so we have to eval e1 under the environment. That'll be v1, which will be a real number. And then we're going to evaluate e2 under the environment. And if that's 0, then what should our total division be? Well, we're going to have this other data type, right? So right now our data types are just numbers. And the other data type is going to be what's called an error. So the idea is that anytime we see an error that comes up, we're just going to pass back an error. And errors can propagate just by sort of absorbing other errors. So this actually leaves room for one extra type of rule, which is, or actually two, right? So we'll have to have eval of div of e1 and e2 under the environment. When else can this be an error? Right, well, if e1, right, if that, we resolve that to say, let's call it v1, which actually turns out to be an error, right? So if the left-hand side is an error, then we'll return an error. And to avoid the short circuiting, we'll make sure to evaluate e2 as well. Right, so that doesn't really matter what v2 is. We're just going to throw an error if e1 is an error. And likewise, there should be one more rule here, which is identical to this, except that it's when v2 is an error. When e1 is not an error, or when v1 is not an error, but when v2 is. And that should cover all of our cases, right? So we'll have when both are numbers, right? When both are numbers, and one is non-zero, and when one is 0, and then we'll have the error cases down here. Right, and likewise, we should write error cases for all of these other, or for plus and mult as well, so that if I have v1 turn out to be an error, I should have this result be propagating the error back up. Right, so eval of plus, I guess let me just write that up here. All right, so to add some error checking, we'll have eval of plus of e1, e2 under the environment. This will be an error if eval of e1 under the environment is an error, right? And doesn't really matter what eval of e2 under the environment is. Let's say it's in a real number. Right, and then there should be one other rule here, which says that if e1 is not an error, but e2 evaluates to an error, then we want to pass that error back up. So this is how we can basically handle, this is the semantics for how we handle arithmetic in this little language. Maybe the one other thing we haven't talked about is, how do we do this ident? So the ident rule is going to look something like this, right? So we're going to evaluate ident of some string s under an environment. And what should this turn out to be? Well, as I mentioned, what is the environment? The environment is this set of mappings, which say like y points to 1.2, x corresponds to 3, z corresponds with 22. And it's just a bunch of ordered key value pairs that we can easily look up. We are going to use the Scala map map data type in order to represent this, same as the dictionary. When we get to the lettuce world, we're going to actually roll our own form of essentially a cons linked list style environment, and that's going to handle what's called scoping, right? So if there's multiple definitions of y in this, how do we know which one to choose? And so what's going to be our rule when we evaluate an ident, right, whose identifier is called s? Well, we're going to look up is s in my environment, in the domain of my environment. Right, so that says, is s one of the things on the left-hand side? And if so, we're going to just get, let's say n.get s. Right, so that should just return whatever s is, and we're going to call that v. And then our eval is going to be v. Right, pretty straightforward. We'll see some of the complications of how to handle environment stuff in the future, but this is enough in order to at least walk through our little example here, right? Which is, what are we doing? We're taking this log of a plus of a constant and a multi of a constant and an identity. So what our eval function is going to do right, let's call this my starting expression e, maybe es for expression start. And we'll have something like eval of es under this environment, right? And let's keep the environment, this guy down here. Sorry, not an equal sign, but a parentheses. And so what do we have? We have eval of something that looks like log of this sub-expression. So this is my e start. This whole thing is going to be e1, right? e1 under the environment. And we didn't write down what the rule is for log, but what do you think it's going to be, right? To evaluate this, I need to evaluate whatever is going on in e1 here. So this guy, so this is the same thing. And then this eval is going to call a sub-eval, that's going to be eval of e1 under the environment. Well, let's rewrite e1, right? e1 is this whole thing here. So we have eval of plus of, I'm going to call this one e2, and this whole thing e3, e2, e3, under the environment. Well, how do we evaluate this? Well, we can look at our plus rule, right? So I have plus of here e2 and e3. So what do I need to do? I need to evaluate e2 first. So first I'm going to call eval, let's do arrows for subcalls, eval of e2 under the environment, right? And what does this do? Or, well, what is e2? This is the same as eval. I'm going to get rid of this little bit here. This is the same as eval of const of 1.0 under the environment. And what did we have for the const evaluation, right? All it did was return 1.0, whatever it was on the inside of the const expression, right? So this is equal to just 1.0. And this is the magic point when we went from abstract to concrete values. It's the point, right, when things start to change. Before we were just sort of eating these abstract ideas. Now we have an actual number going on. So we're going to save that number, right? Because this is now, this v1 here is going to be equal to 1. We see it's a number. We also have another subcall, right, which is going to be eval of e3 under the environment, which if we write that out, right, it's this multiplication of the const of 2.0 and this ident of y. Right, and how do we evaluate this? Well, this guy has some subcalls, right? It needs to, we look over here at our rule for evaluating multiplication. What do we have to do? We have to evaluate the left-hand term first, get a number, evaluate the right-hand term, get a number. So we need to eval const of 2 under the environment, right, which is going to just be 2.0. We also need to evaluate ident of y under the environment. This is the only time we've actually had to use the environment. We keep passing the environment along because we never know when we're going to come across an ident. So it's important to always have it there. That's why I've been very pedantic about making sure that I keep saying environment as we go through. But this is the only time we've actually had to use it, right? So what's our rule for evaluating an ident? Well, I erased it, but what do? We go look in our environment and we look for y. Oh, and I see I found y right here, so what am I going to return? I'm going to return 1.2. And yeah. So that's where we end up using our environment. Okay, so these double arrows are the top of my evaluation for mult. And so now I have, right, this is v1, this is v2 in this format here. So what do I return? I return v1 times v2. So this whole thing turns into 2 times 1.2, which is 2.4. Okay, now what does plus do, right? This was, in our plus rule, this was v1, this was v2. What do we do in our plus rule to evaluate that? We just add those two numbers together. So this whole eval of plus e2, e3 here is going to be, well, 1.0 plus 2.4. So this whole thing evaluates to 3.4. And then we go up to our log rule here, right? So we just figured out what the top of our log rule is, right? The big step is going to be evaluating whatever's on the inside. And now what do? We apply log to whatever value E1 evaluated to, which is 3.4. And that's how our evaluator works on something small like this, right? I mean, it's almost too much to do by hand, which is why this is sort of like the limits of what we're going to be approaching, at least by hand. We'll be able to do a lot more with Scala because we were able to essentially program all of this up really easily and really transparently, so that we can just write this down as a variable statement and then run our eval statement on it, and it will spit out log of 3.4. That's our end goal here. But I hope this was clear enough, right? So we saw what our abstract grammar looks like for basic arithmetic expressions. We saw what some of the evaluation rules look like in this big step semantics and how to write them up, right? They should be fairly straightforward, but the thing you want to keep in mind here is the process of the big step semantics, right? So I am defining what eval does on the bottom left. To do that, I need to calculate everything on the top. And once I've done that, I will have all the component parts that I need to return the thing on the bottom right. So I really like to think of it as sort of stepping up and then back down. Given everything there, typically you say, well, if I know that E1 evaluates to V1 and E2 evaluates to V2, then eval of mult of E1 and E2 is going to be V1 times V2. But that feels like what was E1? Where did E2 come from, right? And it's because we're defining what multiplication means here. I think that's everything I wanted to say about this. We'll see some of the Scala implementation next. Cool. Thanks.